Good morning, everybody. So, in the past few years, we have seen that Wavefield tomography is an effective tool for constructing models. In fact, in the last presentation, Tony showed a very nice example. So, Wavefield tomography constructs models that improve the image quality. Normally, most of the time, this tomography problem is formulated using one-way extrapolation algorithms. So I wanted to look into using two-way extrapolators, and moreover, in cases where we have sharp boundaries in the model. Therefore, what happened in the case of RTM backscattering. So if we see an RTM image in a setting, for example, simulating the Gulf of Mexico, for example, using the 6B model, we see a strong low wave number events above the sharp boundary. This strong wave number events is regarded as noise, and therefore during imaging is eliminated using some sort of filtering step. Let's look at a smaller example based on the 6B model in the mini basin above the salt. So here we have an image with an incorrect sediment velocity, even though we pick the top of salt and we generate RTM backscattering. As you can see here, the RTM backscattering is not as uniform as in the previous image, and it changes sign throughout the section. This is an indication of a velocity error in the sediment section. So if we use Wavefield tomography approach and compute a gradient using this velocity model and this setting, we will obtain something like this. So as you can see here in this gradient, there is a velocity change that will be added to the previous model and optimized through iterations. We see low wave number parts that we expect from a Wavefield tomography gradient, and we also see some crosstalk events that look like reflectors. So now as you can see, there is some link between what we see during imaging and what we see during tomography. Whereas in imaging, the crosstalk produces low wave number events. During tomography, the crosstalk produces high wave number events or reflector-like events in the gradient. So if we apply a filter that preserves the components that we want to the model, we would obtain a gradient like this. So let's go back. Without a filter, with filter, without filter, with filter. So let's go back to the RTM backscattering. So during the conventional imaging condition, we correlate the source wavefield and the receiver wavefield. The source wavefield is normally assumed to be preferentially downgoing wavefield, and the receiver wavefield is normally assumed to be preferentially upgoing wavefield. So when we correlate these two wavefields, we obtain an estimation of the reflectivity. However, if we have a model with a sharp boundary in it, the source wavefield will have a downgoing component to the sharp boundary and an upgoing component from the sharp boundary. And the same goes to the receiver wavefield. So we will have basically two wavefields inside the source wavefield and two wavefields inside the receiver wavefield. So the combination of these four wavefields will produce the total image. And so we can think about the total image as a combination of four different components. So in this much simpler example, you can see an RTM image, and the sharp boundary is just below the last reflector in the model. So two components of this total image, produced by the correlation of wavefields traveling opposite direction, will produce an estimation of the reflectivity. Whereas the other two components that come from the correlation of wavefields traveling in the same direction will produce the so-called RTM backscattering. So now that we understand how this process works during conventional imaging, we can take a look. The next step is taking a look into extended image. So to address the model accuracy of the model of the experiment. So if we take an extension of the image, we can obtain several information about the velocity model. So during extended imaging condition, we are basically correlating two wavefields in space and time. And this tells us information about the similarities of these two wavefields. We want maximum similarity at zero lag, and therefore, if we have energy outside zero lag, we would like to bring it to zero lag. This will ensure that the model is correct, at least for imaging purposes. So as you can see here, this object, there is a general extended imaging condition, increases the dimensionality of the output, the image, in great deal. So if we have, for example, in 3D, and we decide to extend the image in all directions and in time direction, we go from a 3D object to a 7-dimensional object. In 2D, we go from a 2D object to a 5-dimensional object. So what we normally do is use a specific extension, for example, space lag gathers or time lag gathers, or limit this correlation to sparse locations. This is the common image point gathers approach. So let's take a look at space lag gathers and time lag gathers in this simple experiment. And so to your right is the space lag gathers, and to your left is the time lag gathers. So what you see here for low velocity, is that the backscattering now maps vertically into the space lag gathers. So for this low velocity, the space lag gather is undercorrected, and the time lag gather has most of the energy is at positive time lags, thus indicating that the velocity is too low. So if the velocity is correct, we hope that the backscattering will move to zero lag as well as the reflected energy. This means that everything is in synchronization, basically. So this is for low velocity. As we move for correct velocity, most of the energy in the gather moves to zero lag. And for positive velocity anomalies, the space lag gather now is overcorrected, and you can see that the RTM backscattering has a strong presence away from lambda x, and the time lag gather has some backscatter energy at negative taus. So in this very simple example, and in my last year report, so I show that these two parts of the gathers, the backscattered energy and the reflected energy, both contain kinematic information, and they behave in a similar way. So we can use them together in an optimization problem that minimizes the energy away from zero lag. So this is a DSO type of objective function, kind of different to the one that Tony showed just previously, that penalizes the energy away from zero lag. So if the velocity is correct, the residual should be close to zero. For space lag gathers, we can do exactly the same. So we know if the gather is defocused, we will penalize this energy, and we will try to bring it to zero lag through iterations during migration velocity analysis. This approach has been explained the past few years by Tony Yang here and others, for example, Pantin at Rice University. So it has been shown to work very well to obtain good velocity models for imaging purposes. So now, to compute the model update, we use the adjoint state method, as Tony mentioned last presentation. So to do that, well, we first model our source wavefield propagating forward the source signal and the receiver wavefield propagating backward the data. And we construct the adjoint state variables by translating the error measuring the objective function into a source, a joint source, that will carry the model error information. And then we correlate the adjoint state variables with the state variables to produce the gradient. So if the model contains sharp boundaries in it, the correlation of the adjoint state variables and state variables will produce crosstalk events. So what we propose here is to insert a weighting function that depends on the direction of these two wavefields. So how do we preserve this desired direction? Well, we use the approach introduced by Jung a few years ago when in the RTM backscattering removal problem. So here what we use is the complementary part of that filtering approach. Here we want to keep the direction of the wavefields that go in the same direction basically, and discard the correlation of wavefields traveling in opposite directions. So to do that, we use the pointing vector. And well, as you know, to use the pointing vector, you need to stabilize it somehow. So I use a Gaussian smoothing along the time direction with a recursive exponential filter that Dave explained the first day. So if we do that, for example, here I'm showing the weighting function as a function of the angle between the two wavefields. This is how it looks like. So if we have a wavefield, for example, that have similar directions, well, we will have high wave to the wavefield, and then we smoothly taper down to the parts where the wavefield is traveling in opposite direction and produce reflector lags in the gradient. This is an example near normal incidence, for example. So let's go back to the 6B-like example. So this is the true velocity model. As you can see here, we have the sediment section, and the model contains a salt-flooded model below the top of salt. So here we are interested only in the sediments, reflectors, and the top of salt. So if we introduce a fast velocity, in this case this gradient that is overall faster than the true velocity for the sediments, and we construct an RTM image with this velocity, well, you can see that the top of salt amplitude is not uniform throughout the section. In the first part of the around 1 kilometer, for example, the amplitude of the top of salt is very high, whereas as you move down to the deep part of the basin, the amplitude decreases. This is because the error increases with depth, basically. So to understand the velocity error, we can take a look at the extended images. So here I'm showing you space-like gathers. And you can see for the first couple of space-like gathers that the last event, the top of salt, is well focused, whereas as we move down into the basin, becomes defocused and over-migrated. So this again indicates that the velocity is too high. So after we penalize this gather, we obtain a residual that we can then use for Wavefield tomography. So here is the Wavefield tomography residual for the fast velocity. Here I haven't done anything with backscattering because I'm just using the fast sediment velocity model. So what you see here is that, well, we know that since we don't have any reflectors below the top of salt, most of the update should be above the top of salt event. So the gradient is mostly it mostly exists in the sediment part, but it has some parts inside the salt boundary. So what happens if we introduce the top of salt event in the model? So we interpret the top of salt and we perform a salt flooding. So in this case, you can see that the top of salt moved down accordingly with the image. So if we now compute the RTM with this top of salt velocity, this is the first image I show you. So you can see that the backscattering changes throughout the sediment section, and this is an indicator of the velocity error. So if you introduce a top of salt event and then you do RTM and you see this change of the RTM backscattering, this is an early indicator of either the top of salt is grown or the sediment velocity is grown. So if we go ahead and do exactly the same, we take a look at the extended images. Well, we see that the gathers, they show similar behavior. They are nicely focused in the first couple of gathers in the left and the last gather to the right. The top of salt event is nicely focused. And now you can see the backscattering in the extended image. That shows up as vertical events around zero lag. So we can do the same and penalize these gathers to obtain a residual. So this is the gradient that you will obtain using the model with the salt flooding. So here you can see that the energy of the gradient is correctly focused at the sediment part of the model, whereas before we saw some parts that went into the salt. You can also note that the gradient contains a sharp change between sediment and salt. So here the gradient update is basically confined into the sediment section. So if we apply the nonlinear filter to this image, this is what we would obtain. So this is with filter, without filter, with filter, without filter. So as I said before, there is a link between the Wavefield tomography gradient and with what we know for RTM imaging. So the top of the sharp boundary in the model introduces low wave number events, crosstalk, in imaging, whereas for tomography introduces high wave number crosstalk or events like crosstalk. So if we take a look at the difference, well, you can see that we correctly remove what we consider a noise in the gradient coming from the crosstalk between wavefields traveling in opposite directions. And we kept the parts of the wavefield that go in the same direction while preserving some nice features of the wavefield. So we can also try other alternatives. For example, there's a smoothing of the non-filtered gradient. Well, and you can get rid of the crosstalk events, but you also smear the update into the salt model. But the other filter gives us an insight about what's going on and why these events are in the gradient. So we know why they are. They come from the crosstalk of wavefields traveling opposite direction, and so we know how to get rid of those and obtain gradients that are just confined to the sediment section. So this is a comparison again with the filter gradient. You can see that the filter gradient preserves some features that just smoothing smears out. So you might wonder, okay, so what about the top of salt boundary? So if we go ahead with this workflow that is completely different from the normal workflow where we first update the sediments, and once we are confident with the sediment section, where we pick the top of salt and continue downwards. In this case, however, the top of salt, as we update the sediment, the top of salt event will move accordingly. So it will have to be updated at every iteration. However, the top of salt event shouldn't change much from the previous iteration. So we can, I believe, in the value of manual interpretation for top of salt. So we know that is very necessary to get good salt models. So we could go ahead and do that for the first iteration, for example, and for the refine, the top of salt event, and the sediments through iterations. So we can search for the new top of salt event in the vicinity of the previous solution. That could be an approach. There are other automated approaches that I would like to look into that. So, to conclusion, I would like to make the point that the two-way operator we know introduces backscattering. So we could further refine the velocity model, the top of salt, and the sediments using the sharp boundaries. So we would obtain a sediment velocity, an optimized sediment velocity. This is similar to one-way tomography. And if we move the backscattering to zero lag, we would ensure that the sediments model is correct and the top of salt event is also correct. So this could be a tool for QCing top of salt picking and sediments model before continue down into the depth imaging workflow. So as I said, this would be a simultaneous inversion approach where we change both the sediment and the top of salt, and we update at the same time reflected data and the backscattering data. The backscattering data, as you saw, goes to zero lag if the velocity model is correct. This is also true for other type of waves not explored here, as for example diving waves. So if the velocity model is correct, the correlation of this wave should go through zero lag in the image, in the extended image. And as I said before, this requires an automatic salt interpretation approach during iteration. I gave you an idea how to do that. We could search in the vicinity of the previous solution, and we could use, for example, the first solution, manual picking. Or we could explore into, for example, salt cementation algorithms introduced by Lomas and further refined by other SCP student Adam Alpert in the last few years to optimize the top of salt event. So with that, I would like to acknowledge the discussion with Tongning Yang for MBA and Natalia Patekiva for the Pantin vectors. Thank you, and I am happy to take any questions.